Alright, in this video I will talk about the Orientals. So here's an informal definition. The nth Oriental, or n, where this n is a natural number, is the free strict omega category generated by the n simplex. So for example, well, the zero simplex is just a point, so the zeroth Oriental is just a single zero cell with no non-identity higher cells. Or one is the free strict omega category on the one simplex. So this is just a single arrow. And well, the two simplex looks like a triangle. So here's generating data for O2. So it's got three zero cells, three generating one cells, and a single generating two cells in the middle. And well, I said this is an informal definition. So let's make it a little more precise. So this strict omega category, or n, has generating m cells corresponding to the order preserving injections from m to n. So these are the objects m and n in the category delta. That's what I mean by this square brackets notation. So this m is the set of integers between 0 and n with the usual ordering, and same for n. So, well, for example, when n is equal to 0, well, there's only one order preserving injection of this form, namely the identity on 0. So this 0 corresponds to that identity. When n is equal to 1, well, there are two order preserving injections from 0 to 1, namely you can send 0 to 0 or 0 to 1. So these are the corresponding zero cells. And there's one order preserving injection from 1 to 1, namely the identity, which is what this one cell corresponds to. And the same for the case n equal 2. So there are three injections from 0 to 2 corresponding to these three zero cells. There are three injections from 1 to 2 corresponding to the three generating one cells, and the identity on 2 corresponds to this generating two cell in the middle. So the labeling is given by the sequence of integers in the image of this corresponding map. Now, so these are the generating cells of this strict omega category O(n), but I mean, these are meant to be cells, so we have to specify the source and the target of each of these things, and that bit is determined by this rule. So each generating cell points from its odd faces to its even faces. So, for example, if you look at this one cell, 0, 1, so this is the identity, this corresponds to the identity 1. Well, a one simplex has only one odd face, namely the first face. So in this case, if you take the first face of 0, 1, you end up removing this 1. So you end up with 0. So this is the source. And one simplex has only one even face, namely the 0th face. And the 0th face of this 0, 1 is 1. So that is why this arrow points from 0 to 1. And these three generating one cells in O2 are drawn in these directions according to that same rule. And if you look at this two cell corresponding to the identity on 2, well, a 2 simplex has only one odd face, namely the first face. And if you take the first face of 0, 1, 2, you end up with 0, 2. So this is the source of this 2 cell. But a 2 simplex has two even faces, namely the 0th and the second faces. So the 0th face of 0, 1, 2 is 1, 2. The second face is 0, 1. So the target of this 2 cell is the composite of these two 1 cells. So, I mean, at least for these three examples, this rule gave us something that makes sense as the generating data for some strict omega category. But I mean, for higher dimensions, it's not completely clear that all the odd faces actually compose into a single cell, and also all the even faces compose into a single cell, and they are parallel so that you can put a thing in between them. Um, so that is not clear, but that is, well, I mean, I will put a link to the paper, the algebra of Orient simplexes by Wall Street in the description. So if you read that paper or the combinatorics behind the Orientals, and also uh, more explicit descriptions of these ONs. So explicit descriptions not of the generating data, but of the actual cells of these omega categories you can find in that paper as well, although it is a lot of combinatorics. Uh, but anyway, so this is the definition of the Orientals. And why does one want these strict omega categories? Well, usually one constructs these simplex shaped things in general so that, well, together with suitable marks between them, you get a co-simplicial object in your category. In this case, the category of strict omega categories, so that mapping out of them it gives you a simplicial nerve functor. So that's what's on this side of the board. So the simplicial nerve functor induced by these Orientals sends a strict omega category X to this simplicial set whose n simplices are precisely the omega functors out of the nth Oriental into X. So, I mean, this nerve functor is, it exists, but it is not full. So I guess it is well known that in the case of one cat, so just for ordinary categories, the analogous nerve functor is fully faithful. Now, what's happening in that case that's making that nerve functor fully faithful that fails in omega cat? Well, so if you take these pair of categories C and D and take their nerves, well, if you look at the two simplices in the nerve of C, well, they are precisely the commutative triangles in C. And well, the same can be said about D as well. Now, so together with all the simplicial structure maps, the two simplices encode the composition operation in C. Therefore, if you take any simplicial map between the nerves of those categories, it will automatically preserve composition. Well, and the identity is coming from the degeneracy part, but anyway. So in that sense, any simplicial map, because it would send commutative triangles in C to commutative triangles in D, any simplicial map would preserve compositions, and so it will have come from a functor between these categories. Now, if you try to argue the same thing in the case of omega categories, or really for two categories or anything higher than one, well, if you look at the two simplices in the nerve of an omega category, well, I mean, the two simplices are, by definition, the omega functors out of O2 into your omega category. But going back to this side of the board, this is what O2 looks like. In particular, it's got a two cell in the middle, which is, well, just a two cell. This is not necessarily, well, I mean, in this omega category, this two cell is definitely not the identity. And so, well, a strict omega functor out of O2 into your omega category, well, doesn't need to send this tuple to an identity. So what that means is if you look at the two simplices in the nerve of an omega category, you get, well, you do get triangles, but they are not necessarily commutative. So if you take a random simplicial map between the nerves of omega categories, well, I mean, because yes, you have the second component of simplicial map sending two simplices to two simplices, you get a map that sends triangles in C to triangles in D, but it doesn't necessarily send commutative triangles to commutative triangles. So in that sense, like if you consider the corresponding map between the omega categories, it may, I mean, it usually doesn't preserve the composition, and so it doesn't come from a mapping omega cat, so that's why it's not full. But if you want to make, I mean, so the null function is faithful. If you want to make that full, somehow that is the only kind of abstraction. In other words, if you somehow just remember which of those simplices correspond to the identities in your omega category, meaning that the corresponding omega functor out of the Oriental into your omega category sends the unique generating n cell in On to the identity in X. If you just remember which of the simplices correspond to such identities, you get something that is fully faithful. Well, I mean, you no longer land in here because you need that extra information about which of the simplices are special or marked. So that extra bit of information is nowadays called markings. So your new null functor maps into the category of marked simplicial sets. So that marked null functor is now fully faithful, and its essential image is bound by what's called the strict completable sets. But more on those in a different video.